Hello, in this video we're going to be working on problem 3 from the additional tutorial I uploaded. So this is the LP given. It's a production plan LP with 3 products and 3 resources. And we are given the final simplex tableau, and we can tell that it's the optimal tableau by looking at the C bar row, as it only contains 0 or negative numbers. The first question is provide the dual LP and the primal and dual solutions. So we're gonna start by providing the dual optimal solution. We start with the objective function. Okay, so in the primal we have a maximization objective function. So the dual is a minimization objective function. So I'm gonna call it W. So mean W equal to the coefficients of the dual objective functions are going to be the right hand sides of each of the 3 constraints. So we're gonna have 90 y1, which is the first dual decision variable, plus 50 y2 plus 80 y3. Okay, now to the constraints. The first constraint is going to be 2y1 plus y2 plus y3, 2y1 plus y2 plus y3. So here the sign we're going to have depends on the sign of the decision variables in the primal. We can see that x1, x2, and x3 are greater than or equal than 0. So the constraints, all the constraints in the dual are going to be following the canonical form of minimization, which is greater than or equal, and the right hand side is going to be the coefficient of the first variable in the primal. So greater than or equal to 50. We're going to be doing the same thing for the remaining constraints. So for the second constraint we have y1 plus 2y2 plus y3, and again greater than or equal 20. Third constraint, we have y1 plus y2 plus y3 greater than or equal to 30. Now for the signs of the dual decision variables. So as you can see here in the primal, all the constraints follow the canonical form of maximization. Hence we're going to have all the decision variables in the dual greater than or equal to 0. So y1, y2, and y3 are all greater than or equal to 0. Okay, so we now have our dual LP, and now we move to the second part of the first question, which is providing the primal and dual optimal solutions. So if we look at the optimal tableau, we can deduce the values of all the variables. So when deducing the primal solution, we're going to be looking at the right hand side here. So x1 is in the basis and its value is 40. x2 is not in the basis, so its value is 0. x3 is in the basis and its value is 10. s1 not in the basis, so it's 0. s2 also not in the basis. s3 is equal to 30 and z is equal to 2300. Now for the dual solution. For the dual solution, we're going to be looking at the C-bar row in the optimal tableau. So the values of y1, y2 and y3 are going to be the values of the C-bar values of S1, S2 and S3 multiplied by -1. We already know that y1, y2 and y3 are positive, so we're going to multiply these values by -1. So y1 is going to be 20, y2 is 10 and y3 is 0. For the values of e1, e3 and e2 and e3, which are the surplus variables in the dual, they're also positive, so we have 0 for e1 and 20 for e2 and 0 for e3. Now for the objective value of the dual. As we already know from the duality theorem, we know that when optimality is achieved, the objective value of the optimal objective value of the primal is equal to the optimal objective value of the dual. So W is equal to Z, which is 2300. Now for the second question, it says you may acquire at the same cost 1 unit of resource A or 2 units of resource B or 3 units of resource C. Which resource will you buy and at what maximum additional cost? Now we're talking about the shadow prices, obviously, which are the marginal unitary value of a resource. So for resource A, the marginal value of 1 unit is $20 or dinars or whatever. For resource B, it's 10, and for resource 3, it's 0. So for resource 3 or C, I'm not interested in acquiring any additional units since its shadow price is 0, so it's not worth anything to me. And when you look at the basis, it makes sense because we have S3 in the basis and it's equal to 30. So I have 30 units of resource C that I'm not using, so it doesn't really make any sense for me to want to acquire additional units of that resource. Now for resources A and B, they're not in the basis, so we don't have any units of resources A and B after the production process. So it would make sense for us to want to acquire additional units. When we compare the two, the first resource A, has a higher shadow price. It is 20 and 10 for resource B. But in the question, it says that we can acquire either 1 unit of resource A or 2 units of resource B with the same price. So for us, it's the same. So we are neutral about acquiring either 1 unit of A or 2 units of B. I went ahead and wrote down the answer, and I will make sure to send you the notes later. So now for question 3, it says, if it is possible to improve the profitability of product 2, what would be a reasonable profit rate so that this product will be incorporated in the production plan? Okay, so product 2, as you can see, is not in the basis. So we're not producing any units of product 2. And the question is about how to make it more profitable. So if we look at the C bar row, we can see that the reduced cost of product 2 is 20. This means that if we increase the original profit rate of product 2 by 20, it's going to be profitable and could be incorporated in the production plan. So to answer this question, let's see how much it costs how much the profit rate of product 2. It's 20. So a profit rate, a reasonable profit rate of product 2 would be 20 plus 20, which is $40. Okay, so now question 4, it says, if it is possible to reduce the consumption of product 2 in resources, what would be a new consumption alternative that would make product 2 profitable? So to answer this question, we are going to be looking at the dual LP, and specifically at the second constraint, as it represents the product 2's consumption of each resource. In case this was not obvious to you, you may want to watch the part where we built the dual LP again. So to make product 2 more profitable, its consumption of resource, or the left hand side of this constraint, should be lower than its profit rate, which is the right hand side of the resource of the constraint. And that would mean that this constraint would have to be violated. So in order to for this constraint to be violated, we're going to have to first to find new coefficients that would make the left hand side of this constraint smaller than its right hand side. And this is pretty much a trial and error process. With the coefficients we currently have, the left hand side of this constraint is actually 40, which satisfies the constraint since it's larger than the right hand side. In order to make the left hand side smaller, we're going to have to modify these coefficients, well, mainly these two, since the optimal value of y3 is 0, so it won't change. This coefficient will not change anything. So let's start by dividing them by 2. So let's make this 0.5 and make this 1. Well, it's still equal to the left hand side, so we're gonna have to lower it just a little bit. So 0.4. Yes, now we have the left hand side smaller than the right hand side, which means that the constraint is violated, which means that the consumption of product 2, the consumption of resources of product 2 is less than its profit rate, which makes it more profitable. So to answer the question, the consumption the consumption of product 2 that would make it profitable would be 0.4 units of the for resource A and 1 unit of research 2. We now go to question 5, which is, what would be the effect of the following two new constraints on the optimal production plan? And these two constraints are x2 less than or equal to 10 and x3 less than or equal to 10. Okay, so to verify the impact of these constraints on our optimal solution, we first have to plug in our optimal solution and see whether or not they're satisfied. So the optimal value of x2 is equal to 0, which is less than or equal than 10. So the first constraint is satisfied. So it would not change anything if we introduce this constraint to our LP. It will not change anything. For the second constraint, the optimal value of x3 is equal to 10, which satisfies the constraint. So the second constraint is also satisfied, and hence by introducing these two constraints into our LP, nothing is going to change. The optimality is preserved. Okay, now question 6. If product 1 profit rate decreased to 40, what would be the new optimal solution? Well, the current profit rate of product 1 is 50, so it's gonna be going down by 10. So I'm gonna call this change in the the change in the coefficient in the objective function of x1 delta 1. Okay, so if you look at the optimal tableau, you can see that x1 is a basic variable. It's in the basis, and hence any change to its coefficient in the objective function will cause the C-bar values of the non-basic variables to change. Non-basic variables here are x2, s1, and s2. Okay, so in order to preserve the optimality of this tableau, these values have to remain less than or equal to 0. So we're going to recalculate the C-bar values of the non-basic variables using this formula, and we're going to make sure that they are still less than or equal to 0. So the new C-bar value of x2 is minus 20 minus the value in the row of x1, so it's minus 1, so minus and minus is going to be a positive sign, plus 1 multiplied by delta 1. Okay, so this new value has to be less than or equal to 0 in order for the basis to remain optimal. Now for S1, we do the same thing. So it's minus 20 minus 1, because the value in the x1 row is 1 and not minus 1. So minus delta 1 This one also has to be negative. And for S2, the new value is minus 10 minus 1, so it's plus delta 1. This one has to be less than or equal to 0. So in order to find the range in which delta 1 could move and the basis would remain optimal, we're gonna have to solve this system. It's very basic math. So this one, we just take this 20 and put it on the other side. So after solving this system, we find that delta 1 is between minus 20 and 10. And this means that as long as we do not increase the profit rate of product 1 by more than 10, and we do not decrease its profit rate by more than 20, optimality shall be preserved. So in question 6, we have delta equal to minus 10. So minus 10 is between minus 20 and 10, which means that optimality is preserved. Okay, now for the last question, we're going to study the effect of a change in resource B availability on the optimal basis. So I'm going to be calling the change to the availability in resource B delta B, and we're going to study its effect on the variables in the basis. So we know that for the basis to remain feasible, the values of the right hand side have to remain greater than or equal to 0. So this first. And we also know that the parameter delta B and S2 have the same coefficients in the standard form and continue to have the same coefficient until the optimal tableau. So this new value of x1 have to be 40 minus delta B So this value have to be greater than or equal to 0 for the basis to remain optimal. The second value is 10 plus 2 delta B and it also needs to be greater than or equal to 0. Third value is 30 minus delta B, also needs to be greater than or equal to 0. So we have this system, and by solving it, we can deduce the range in which delta B has to be in order for this basis to remain optimal. So after doing the calculations, we deduced that delta B is between minus 5 and 30. So we conclude that as long as we do not increase the availability of resource B more than 30 units and we do not decrease it by more than 5 units, our optimal basis is going to remain optimal. This is it for this problem. I hope it was clear. Please let me know if it's not, and thank you very much for listening.